In a previous video, we talked about functions as a special sort of relation, namely with each input having a unique output. And in this video, we're going to be talking about equivalence relations, which are going to be another special sort of relation which captures some of our intuition about what it means for two things to be equivalent to one another. So as I claimed, we have some prior intuition about what it means for two objects to be either very similar or even congruent to one another. And we had this sort of intuition early on in math when we talk about things like triangles being congruent to one another, or even in multivariable calculus or linear algebra when we say that vectors are equal to one another. And one particular sort of congruence is when we use the word equal. And let's go with this analysis of the word equal for a second. So as we all know, there are some very essential properties about two objects being equal to one another, even one object being equal to itself. So one property that, well, it seems pretty self-evident, is that if you have some object x, it's equal to the object x. And we're going to give the name to this property, and we're going to call it the reflexive property, or we're going to say that this expresses reflexivity. So a second property that we experience is that if x is equal to y, then y is also equal to x. And we're going to call this the property of symmetry. And the third and final property that I'd like to look at is called transitivity. So with this, we say that if x is equal to y, and if y is equal to z, then those two statements together, if they're both true, then that applies that x is equal to z. And we're going to call that the property of transitivity. So these are the three properties that we're going to end up abstracting out of the notion of equal. So what I propose we do for this discussion is we abstract those three properties about the notion of equality. But instead of using the term equal, let's start using the term equivalent or congruent. And we're going to take those properties and we're going to apply them to relations. So instead of saying only x is equal to y, we're going to say that x is very, very similar, or let's say that x is equivalent to y. So having talked about those three properties of reflexivity, symmetry, and transitivity, what I'm going to do is define an equivalence relation using the symbol r on some set A as a binary relation on A. And remember, that means it's just R is a subset of A times A, which also has three additional properties for all the x's and y's within the set A. So first, we're going to say that Rx for all x within A. So we're going to say that this is, again, that reflexivity property. The second property, that x r y if and only if y r x, and again, that's the symmetry property. And the truth of x r y and y r z taken together implies that x r z. And this is the transitivity property. So we're going to say that a relation R with these three additional properties is a special sort of relation, and we're going to call this an equivalence relation because it harvests those three properties that we expect out of equivalence. So to give a tangible example of what an equivalence relation is going to be doing, let's consider this some set A, which is just going to be the numbers 1, 2, 3, and so on, all the way up to number 12. And what I'm going to do is I'm going to partition or divide the set into three different groups, or three separate divisions. I'm going to call those A1, A2, and A3. And the way I'm going to partition them is just to take the first four numbers, 1 through 4, stick them in the set A1, the next four, 5 through 8, stick them in A2, and the final four, 9 through 12, and stick them in the set A3. So I partitioned that set A into three separate divisions. So what I'm going to do is say that if I pick any two elements, x and y from A, I'm going to say that those two elements are equivalent if and only if they're in the same division. So just to make that clear, x is equivalent to y. I'm going to use this tilde symbol to mean equivalent in this sense. So x is equivalent to y if and only if x and y are in the same division. So from that definition, what I can see is that 1 is in the same division as 1. There's 1 right there in A1, and 1 is indeed in A1. So 1 is equivalent to 1. 1 is equivalent to 2, because 1 and 2 are both in A1. And going further, 2 is equivalent to 3, and 1 is equivalent to 3, and so on. You can see there's a bunch of relations that are going to be going on here if I say this is what I mean by equivalent. And you can verify for yourself that this relation, which I'm expressing by this symbol, is indeed an equivalence relation. Something's going to be in the same set as the same division as itself. So that's the reflexive property. If I have, let's say, 1 and 2 being in the same division, then certainly 2 is going to be in the same division as 1, so I have symmetry. And furthermore, I have transitivity, because if, let's say, 1 is in the same division as 2, 2 is in the same as 3, then 1 is indeed in the same division as 3. So I have all the 3 properties I need for an equivalence relation. So what I conclude from this is that this partition induces an equivalence relation upon A. Now let's think for a second in a more general sense. Now suppose I pick some element x from A, and I want to list all the elements that are said to be equivalent to x with respect to some equivalence relation R. So now I'm going to introduce this notion of the equivalence class of x modulo R, which I'm going to denote by this symbol. I'm going to read this as the equivalence class of x mod R. And what that's going to be is going to be all the members T such that x are T. So this is the symbolic form of just what I was saying up here. I'm going to list out all the elements T that are said to be equivalent to x. So if I go back to the previous example, where I have that partition into 3 divisions, let's look at the equivalence class of 2 with respect to that equivalence relation tilde. So we can see that that equivalence class is going to be 1, 2, 3, and 4, because all 4 of these elements are said to be equivalent to 2, and they're equivalent to 2 because they're in the same division. And hopefully it's obvious that this set is also equal to A1. So the equivalence class of 2 mod tilde is equal to A1. And just continuing with some of the other elements, you can also see that the equivalence class of 4, all the stuff that's said to be equivalent to 4 mod tilde, is also equal to A1. So we can see immediately that the equivalence classes of 2 and of 4 mod tilde are equal. And just continuing with another example, the equivalence class of 6 is the same as that of 8, which are both equal to this division here, A2. And one final note when talking about equivalence classes is that in this particular example, if I take the equivalence classes 1, 5, and 9, and I just union all those together, I can reconstruct all of A, because these equivalence classes partitioned up A, and if I unite those partitions together, I just get what I started with, which was A. And one final terminological note here is that up here I was saying equivalence class is mod tilde, and I was writing the tilde as a subscript here. But if I drop that, you'll sometimes see people drop the subscript, and you're just going to have to figure out what the equivalence relation is just from the context. So in this context, it's pretty clear what I'm talking about in terms of equivalence being in the same division, but you'll just have to infer that from the context. One idea I'd definitely like to point out is that the notion of equivalence relations allows us to partition up sets, and that the idea of partition of a set induces equivalence relations. And I hope that second statement, that the idea of partition induces equivalence relations, was clear through that example where I partitioned up the set A. So if you get nothing else from this video, hopefully you can start to see this idea as we go through the video, that the idea of partition of a set and the idea of equivalence relation, those two ideas are very intimately connected to one another. So let's go back to the example of the set A being the numbers 1 through 12, and the notion of equivalence being represented by that symbol as being in the same division. Now what we could have done is just, we could have taken all the members from the set A and create a new set, let's call it C for now, where each of the members of the set is the equivalence class, mod tilde. So what I'm doing now in this experiment is I'm taking all the members here, and I'm just taking their equivalence classes. Now one thing we noticed that when we were analyzing all the equivalence classes is that some of them were identical to one another. Namely, the equivalence class of 1 was the same as 2. And if you continue that out further, you would see that 2 is equal to 3, the equivalence class of 3, equivalence class of 3 is equal to the equivalence class of 4, and so on. And if you go analyzing the other one, the equivalence classes of 5, 6, 7, and 8 would have been the same. And the equivalence classes of 9, 10, 11, and 12 would have been the same. So what that means is that even though superficially this set C here appears to have 12 elements, what ends up happening is that you get all the redundancies trimmed out to only 3 elements. So the set C only has 3 elements now, the equivalence classes of 1, 5, and 9, mod tilde. So what is this idea that I just expressed? It was namely that the 3 elements of C the equivalence classes of 1, 5, and 9 partition A with respect to this equivalence relation tilde. So if you were to write out these sets, these would be precisely those partitions. Like the first 4 elements would be listed here, the second 4 would be listed here, and the third collection of 4 elements would be listed here. So here, hopefully you can start to see that notion of partition being induced by equivalence classes. So what I'm going to do now is I'm going to introduce a new idea. So suppose I have some set A and some equivalence relation, let's call R, on the set A. I'm going to say that the quotient set A modulo R is, and it's going to be represented by A slash R, is equal to the set of all the equivalence classes mod R, such that the x's are in A. And you can see that's precisely what I've done up here when I formed the set C from the set A. And hopefully you can also see that when you do this, let's say A has 12 elements here, that doesn't necessarily imply that C is going to have 12 elements. In fact, in this case, C had only 3 elements. So the C, what I just formed up here, is going to be A modulo tilde. So now we've defined the quotient set. So let's now talk about functions involving the quotient set. So let's go back to the set A. We had those members 1 through 12. Let's say I take each one of those members of A. Let's say I take those first 4 members, 1, 2, 3, and 4, and I associate them through a function to the equivalence class of 1. And why am I doing that? Because 1 is going to be in the equivalence class of 1, 2 is also going to be in the equivalence class of 1, and so are 3 and 4. So what I'm going to do is I'm going to send all 4 of those numbers to the equivalence class of 1. And I'm going to do a similar sort of thing for the next 4. I'm going to send them to the equivalence class of 5. And I'm going to take the numbers 9 through 12 and send them to the equivalence class of 9. And hopefully you can see why I'm starting to do this, because all of the numbers within each particular division are members of that equivalence class, modulo tilde. And what I'm going to do is I'm just going to call that function that I just assigned to each one of these numbers between A and A modulo tilde. I'm going to give that the name phi. And another name for this is the canonical mapping, or the natural mapping between A and A modulo tilde. And hopefully you can see that this is indeed a mapping between A and A modulo tilde, since the domain of phi is all of A. I've assigned, for all the members of A, those have been assigned a value, and that the range of phi is a subset of A modulo tilde. And later we're going to show that the range is actually equal to all of A modulo tilde, but hopefully you can see that it's at least a subset of A modulo tilde. So as I hinted before, we're going to define the canonical mapping phi from the set A into, and I'm going to claim onto, the set A modulo tilde, and that's going to be given by phi of any particular x is going to be equal to the equivalence class of that x modulo tilde. So you can see I can go through the long process of doing 1 being sent to the equivalence class of 1, 2 being sent to the equivalence class of 2, 3 being sent to the equivalence class of 3, but when I observe that the equivalence classes of 1, 2, 3, and 4 are all the same, what I can do is I can say that that's the same thing as sending all 4 to the equivalence class of 1. So those two mappings that I just expressed, those are going to be the same thing. But just to make that clear, suppose I were to write out this function phi. So remember, the functions are just going to be a set of ordered pairs. And what that would look like is that 1 gets sent to the equivalence class of 1, 2 also gets sent to the equivalence class of 1, 3 would be sent to the equivalence class of 1, and so on. And then, just as another example, 10 is going to be sent to the equivalence class of 9. So now I'd like to prove an important theorem that relates the ideas of equivalence with equivalence classes. And the theorem is going to be, for all the x's and y's within some set A, and let's suppose R is some equivalence relation on A, the fact that x and y have the same equivalence class implies that x is equivalent to y, and vice versa. The fact that x is equivalent to y, or x are y, implies that the equivalence classes modulo R are the same. So it's an if and only if statement, so we've got 2 statements to prove. So let's first suppose that the equivalence classes are the same. So here I have the equivalence class of x mod R is the same as the equivalence class of y mod R. So what we know is that, and this is going to be true for any equivalence class, is that x is always going to be in the equivalence class of x. And that's coming from that reflexive property that x are x. So x is always going to be in the equivalence class of x. And by assumption, I'm assuming the equivalence class of x is the same as the equivalence class of y. So that x is also going to be in the equivalence class of y. Now, what this statement means is that y are x. And since I have the symmetry property, y are x implies that x are y. And that's exactly what I'm trying to show, that x are y. So that's hopefully pretty straightforward. So let's now prove the converse, that x are y. The fact that x are y implies that the equivalence classes of x and y are the same, modulo r. So what I'm going to do, in order to prove that two sets are equal, I'm going to have to show that they're subsets of one another. So first, let's suppose I have some element z within the equivalence class of x. So, just by the meaning of the equivalence class, x are z, and since r is an equivalence relation, I have symmetry. So x are z implies that z are x. And since I have the truth of z are x, and I also have the truth of x are y, by transitivity, I have z are y. And again, just switching stuff around, I have symmetry again. Z are y implies y are z. And just from the meaning of this statement and the meaning of equivalence class, this statement implies that z is an equivalence class of y. So what I've just shown is that z being in the equivalence class of x implies that z is also in the equivalence class of y. Therefore, the equivalence class of x is a subset of the equivalence class of y. And the statement to show that the equivalence class of y is a subset of the equivalence class of x is very similar. So I'll just go through it. Suppose I have some z in the equivalence class of y. Just by the meaning of that statement, y are z. By symmetry, z are y. And now, since I have the truth of x are y, I also have the truth of y are x. So I have z are y are x, and by transitivity I have z are x. By symmetry I have x are z. And by the meaning of this statement, and by the meaning of the equivalence class, I have that z is in the equivalence class of x. So hopefully you can see that shows that the equivalence class of y is a subset of the equivalence class of x. And from those two conclusions, the equivalence class of x is a subset of the equivalence class of y, and the equivalence class of y is a subset of the equivalence class of x. I can see that those two sets are equal. But apart from moving symbols around and whatnot, I think this statement here is very, very important for this idea of equivalence classes and equivalence relations, is that if two things have the same equivalence class, then they must be equivalent to one another. So that's the first theorem I'd like to prove, and here's the second theorem I'd like to prove. So suppose f is some function, let's say from the set A to the set B, and let's say we have some equivalence relation tilde, which I'm going to define in a different way for some x and y with an a. I'm going to say that x is equivalent to y if and only if their function outputs are the same, namely that f of x is equal to f of y. And hopefully you can see that this definition is indeed an equivalence relation. It has those three properties of reflexivity, symmetry, and transitivity. And the theorem is going to claim that there exists a unique injective function, let's call this f hat, mapping a modulo tilde to b, such that the combined actions of phi, which is that canonical mapping, and f hat are the same thing as that function f from a to b. So that's the statement of the theorem, but conceptually, what is this saying? It's saying that I have this function from a to b, which is going to map the set A to the set B here, so I can do that directly from the set A to the set B. But the theorem is claiming that another way to take the set A to the set B is to first take the stuff within A, send it to a modulo tilde, where tilde is defined to be as such, where f of x is equal to f of y, send it to a bunch of equivalence classes here in this set, and then have another function, f hat, which is going to take the stuff from the quotient set, and then map it to the set B. And what the theorem is claiming is that this function f hat exists, it's unique, and it's injective. So conceptually, this is what's going on here. Instead of directly mapping a to b, what I can do is I can map a to this quotient set through the canonical mapping phi, and then send all the stuff here to set b. So this is a decomposition of a function of sorts. So this calculation here, that f hat of phi of x is equal to f hat of phi of y, is the same thing as saying that f hat of the equivalence class of x is the same thing as the equivalent of f hat of the equivalence class of y. And that's just because the symbol phi here is sending those x's to the equivalence classes. So this is another way of writing this first line here. So again, what I want to show is that from this statement, I can deduce that the equivalence class of x is the same as the equivalence class of y. So from the definition of f hat, which I propose is going to be up here, this is going to be equal to f. So the left-hand side is just f of x, and the right-hand side is just f of y. But then I defined that the f of x is equal to f of y to mean that x is equivalent to y. So this statement implies that x is equivalent to y. And from the theorem I showed before, if two things are equivalent to one another, their equivalence classes must be the same. So what I've done here is I've said that f hat of the equivalence class of x being equal to f hat of the equivalence class of y implies that the equivalence classes of x and y are the same. And that shows that f hat is indeed injective. So next I'm going to show that special function f hat is unique, in the sense that there's no other function that has the same action as f hat of phi. So the way to show that symbolically is to suppose that there is some other function, I'm going to call that g hat, that has the same action as f hat of phi. So I'm going to say that suppose f hat of phi is the same as g hat of phi. And what I want to show is that no, those two things, f hat and g hat, were really the same thing, which shows that the function is unique. So first, to show that, what I'm going to do is I'm going to show that this canonical mapping phi from a to a modulo tilde is surjective. And I want to show that it's surjective because what I want to do is show that if it's surjective, that there's a right inverse, and I'm going to essentially cancel out the action of phi from the right-hand side, and I'm going to be left with the statement f hat is equal to g hat. So in order to show that phi is surjective, I'm going to have to show that the range of phi is all of a modulo tilde. So in order to show that, I'm going to say, well, let me pick some element t, the equivalence class of t, from a modulo tilde. So if phi is going to be surjective, I should be able to find some element within the domain of phi such that that thing combined with the equivalence class of t is within the function phi. That's just what it means to be surjective. But I always know this is true, that t is always in its own equivalence class. So if you give me any element from this set, a modulo tilde, there's always a domain element that gets mapped to the equivalence class of t. Namely, it's t, the equivalence class of t being in phi. So that implies that phi is surjective. And phi being surjective implies that phi has a right inverse. And I showed that in the previous video on functions. Let me call that right inverse phi minus 1. So what I'm going to do is I'm going to go back to the statement that f hat of phi is the same thing as g hat of phi. And what I'm going to do now is apply the right inverse to both sides of the equation. So I have f hat of phi inverse equals g hat of phi inverse. And since this inverse exists, the action of phi inverse is just the identity operator. So when I apply that right inverse to both sides, I'm just going to get f hat of the identity is equal to g hat of the identity. And that, of course, implies that f hat and g hat are the same thing. So hopefully, besides knowing how to prove the theorem, we could trying to understand what it's saying conceptually. So let's take an example. Let's say I have some set A. It's got -2, -1, 0, 1, and 2 in it. And let's say f of x is equal to x squared. And again, I'm going to define the equivalence relation tilde as the following. X is equivalent to y if and only if x and y produce the same function value. So you can see I picked the squaring function here just because -2 and 2 are going to produce the same function value, just like -1 and 1 are, and just like the opposites of a number are going to produce the same function value when you square them. So under this definition, we can observe that 1 is equivalent to 1. Something is equivalent to itself. 1 is equivalent to -1 because they produce the same function value, and 2 is equivalent to -2. So let's say we're going to write out what f is doing explicitly. It's mapping this set onto another set. So what it's doing is it's taking -2 to the value 4, it's taking -1 to the value 1, taking 0 to 0, 1 to 1, and 2 to 4, just by squaring. But from the last theorem, what we want to see conceptually is that you don't have to go directly from -2 to 4. You can go to that intermediate set, a modulo tilde, and then create another function, f hat, which takes a modulo tilde to that other set, which is going to contain numbers like 4, 1, 0, and so on. So what I can first do is apply the function phi to the elements of the set A. So what I'm going to do is I'm going to send both -2 and 2 to the equivalence class of 2. And remember, these two are equivalent, so they're going to have the same equivalence class. So the equivalence class of 2 and -2 are going to be the same. I'm going to send -1 and 1 both to the equivalence class of 1. And I'm going to send 0 to the equivalence class of 0. So what I've done is I first applied phi. So in order for f hat to be the same, or for the action of f hat of phi to be the same as the function f, what I'm going to have to do is let f hat do the following. It's going to have to take those equivalence classes. Let's take the equivalence class of 2, for example, and it's going to have to send them to the common value of the stuff within the equivalence class. So what I'm going to do is I'm going to send the equivalence class of 2 to the number 4, the equivalence class of 1 to the number 1, and the equivalence class of 0 to the number 0. So hopefully you can see that this function composition here, f hat of phi, is doing the same thing as f for any starting value within the set A. So again, just the f hat is going to map the entire equivalence class, not the numbers within the equivalence class, but the entire equivalence class, to the common value of f of x among its members. And there are many ways of looking at this. The way I see is that what's going on is that tilde, the equivalence relation, is going to partition A into a modulo tilde. In other words, it's going to make this set, it's going to make a modulo tilde as this partition -2, 2, and then -1, 1, and then 0. And then this special function f hat is going to take these entire objects, the set -2, 2, which is the equivalence class of 2, and it's going to send it to the common value of f of x among these members, which was 4. So hopefully conceptually you can start to see what's going on in this function composition here. So that wraps up this video on equivalence relations, and here are the practice problems for this video. And make sure to stay tuned for the next set of videos where we're going to develop the set theoretic foundation for natural numbers, and we're going to talk about inductive sets. So as always, thanks for watching. If you enjoyed the video, give it a thumbs up. Feel free to subscribe, and thanks again for watching.